Okay, in our last segment, we learned about reflection and refraction. So now we're going to put this to use in trying to discover where is the boundary between the crust and the mantle. So in our picture up here, we're trying to find this region right here between the crust and the mantle, and this is going to be called the Moho. Okay, the Moho is going to be short for Mohorovich discontinuity. And so from now on, I'm just going to refer to that as the Moho. So this was named after the guy who discovered this boundary. Okay, now the idea is going to be that here's the surface of the Earth. Okay, here is going to be the boundary between the crust and the mantle. And then let's say that for some reason an earthquake is going to occur right here. And so that means it's going to send out earthquakes, waves this way, and this way, and this way, and this way. So it's going to send out earthquake waves in all directions. Now let's assume that we have a seismic station that is going to be located here. So that some of these seismic waves are going to travel like this. So they're going to be refracted as they go through the Earth, and they're going to arrive at that seismic station. Now, what do we know about the speed of earthquake waves? So they're going to travel faster through more dense rocks. So they're going to travel at a certain speed through the crust and then get to that seismic station. Well, some of these earthquake waves, though, are going to go into the mantle, curve around, and then come back up to the seismic station. Now notice that this, if it goes this way, it's a shorter path than going this way. And so it doesn't make any difference what the difference in the speeds are between the waves in this region and the waves in this region. These waves are going to get there first because it's just plain the closest way. Now on the other hand, what about if there was a seismic station located over here? And what's going to happen this time is that these waves are going to travel directly, and some of the waves are going to go through the mantle and then come back up. Well, this time there's going to be a difference. So the first time, the waves that traveled through the crust got there first. And then the second time, though, these waves going this way are going to arrive first because they can travel faster through the mantle. And so this scientist was able to discover, by having multiple seismic stations and measuring the arrival times of these various kinds of waves, he was able to figure out what was the depth to the mantle. And then that turns out to be the Moho. Okay, another thing that is about the boundary between the crust and the mantle that is important is that the Moho is going to be deeper underneath the continents than what it is going to be the oceans. So if we were to draw a picture of this, let's say that this is continental lithosphere, and let's say that that's a mountain. Well, one thing that we're going to find out later is that it's going to be the principle of isostasy, where a mountain is going to have a root. And so that root is going to go deep into the mantle. So this is continental lithosphere, and notice that the distance from the surface down to the Moho can be very deep if you're talking about continental lithosphere. But if we continue this on into the oceans, we found out that oceanic lithosphere is much thinner because it's more dense. So this is less dense granite that's making up the continents. This is more dense basalt, and so oceanic lithosphere is going to be thinner than continental lithosphere, and so therefore the distance from the surface down to the Moho is going to be shorter here than what it is on the continents. Okay, so In our next segment, we are going to explore now what's going on in the mantle. And so I will see you in just a few moments.